Hello students, in this class we shall discuss about the depression of freezing point. So this diagram, it depicts the variation of vapor pressure of pure solvent and that of the solution of a non-volatile solute in it as a function of temperature. The vapor pressure of solution of a non-volatile solute is in volatile solvent is always lower than that of the pure solvent. See here, so this solution, it is mixed with non-volatile solute, hence the vapor pressure of the solution is lesser compared to this pure solvent. A liquid freezes at a temperature when the vapor pressure of the solid solvent becomes equal to the liquid solvent. So whenever the solid solvent and the liquid solvent's vapor pressure becomes equal, then we are going to get the freezing point of a solution. So this point is the freezing point of solution. It is lesser than the solvent. Let this T0F be the freezing point of pure solvent and TF be the freezing point of this solution. So this freezing point of solution, it is lesser than the solvent. Now delta TF, that is the freezing point depression constant, that is freezing point depression. So if you want to calculate this delta TF, so the difference, that is delta TF is equal to T0 F minus TF. So this is known as depression of freezing point. Again, as in the case of elevation of boiling point, the depression of freezing point for a dilute solution is directly proportional to molality of the solution. So this delta TF, it is directly proportional to molality of the solution. Now if I remove this proportionality term, so this delta TF is equal to, I need to introduce one constant term, I will take KF for freezing point into molality. So where this KF is known as freezing point depression constant or molar depression constant, or even it is called as cryoscopic constant, and this M, it is the molality of the solution. Now if M, that is molality, if it is equal to unity, if it is 1, then Kf will be equal to delta Tf. That means that the molar depression constant, that is equal to depression in freezing point. So how we can define this molar depression constant? So molar depression constant of a solvent is the depression in freezing point caused by dissolving 1 mole of non-volatile solute in 1000 gram of the solvent. So here we have dissolved 1 mole of non-volatile solute in 1 kg of the solvent. So that is why it is called as molar constant. So 1 kg is nothing but 1000 gram. Now again, if I consider two components, component A and component B. So component A is our pure solvent and component B is non-volatile solute. So if WB gram of a non-volatile solute having molar mass MB is dissolved in WA gram of a volatile solvent. So by definition of molality, so molality of the solution this is equal to 1000 divided by WA into WB divided by MB. So this is WB is the mass of non-volatile solute, MB is molar mass of solute, WA is mass of the pure solvent. Now, depression of freezing point, that is delta TF, this is equal to KF into M. Now if I substitute the value of M in this equation, then delta TF, this is equal to KF into 1000 into WB whole divided by WA into MB. Now I will rearrange the terms, that is delta TF is equal to 1000 into KF into WB mass of solute divided by mass of solvent into molar mass of the solute. Now if I want to determine the molar mass of the non-volatile solute, then MB is equal to 1000 into KF into WB divided by WA into delta TF. So from this equation we can determine the molar mass of non-volatile solute knowing WA, WB, KF. The molecular mass of solute can be calculated after determining the value of delta TF experimental. Now, to calculate the KF value and KB value, molar elevation constant and freezing constant. So we can calculate with the help of these equations, that is R MA TF square divided by 1000 into enthalpy of fusion to calculate KF value, where R is the universal gas constant, that is 8.314 Kelvin kg per joules per Kelvin, joules per Kelvin per moles, and Ma is the molar mass of the solvent, TF square 1000, and delta H of fusion, that is enthalpy of fusion. Similarly for Kb value, that is Kb is equal to R into Ma Tb square divided by 1000 into enthalpy of vaporization. Since it is the boiling point, we will take the vapors, that is enthalpy of vaporization. It is, since it is freezing point, we will take the fusion. So R value, that is 8.314 joules per Kelvin per mole. Ma is molar mass of the pure solvent. So delta H, that is enthalpy of vaporization. From these two equations we can calculate the Kf value and Kb value. So here are some of the values of the molar depression constant for some solvents. So water, it freezes at 0 degrees Celsius, that is at 273.15 Kelvin, and its Kf value is 1.86. Even the Kf value is, unit of Kf value is same, that is Kelvin kg per mole. Even it is for same for Kb. Here Kb for unit of Kb is also Kelvin kg per mole, and it is same for Kf. Ethanol, it freezes at 155.7 Kelvin and its Kf value is 1.99. Cyclohexane freezes at 279.55 and its freezing point is 20. Benzene, it freezes at 278.6 and its Kf value is 5.12. Chloroform freezes at 209.6. Its Kf value is 4.79. And carbon tetrachloride, it freezes at 250.5 and its Kf value is 31.8. Carbon disulfide freezes at 164.2. Its Kf value is 3.83. Thank you.